So today we're talking about exponential growth and decay, and I want to start out just by looking at what exponential functions look like. So here we have f of x equals a times b to the power of x. When you're writing an exponential function to match a real-world scenario, a is going to be your initial value most of the time. That's your y-intercept of your graph. And then b represents your common ratio. And your common ratio could be a value greater than 1 that's going to cause your exponential function to increase with exponential growth, or it could be between 0 and 1, so like a fractional value between 0 and 1 that's going to cause the exponential function to decrease, and we call that exponential decay. Let's look at an example of growth here. Julio purchased a baseball card for $1.25. Each year, the value of the baseball card increases by 15%. All right, so our initial value here, what we started with, is $1.25. So that's A. And then we're increasing by 15%. So our common ratio is going to be 1 plus 15%. 1 plus 15 hundredths. That's 1.15. So we could write the function f of x equals 1.25 times 1.15 to the power of x. And now that we have this function, we can use it to make predictions. So here we're asked, what will Julio's baseball card be worth in 20 years? Well, one way to figure out the answer is just to substitute 20 in place of x, like I've done here. In doing that, I found that it would be $20.46 if he saves that baseball card for 20 years. I could also do it using a graph, and I created this graph here in Desmos. So all I have to do to use my graph is go over to 20 on my x-axis, and then go up and see where that is on my y-axis. And I could estimate that that would be just a little bit over $20, and it is. Remember earlier we found that it's $20.46. So what about decay? Here's a real-world example that most of us are familiar with. Sarah's car is worth $16,500. Each year, the value of her car decreases by 8%. So she started with a value of $16,500. That's our initial value here, and it's decreasing by 8%. So what we're going to do with that decrease is subtract it from 1. So 1 minus 8 hundredths equals 92 hundredths, or 0.92. So then when we write our function, we're going to have f of x equals 16,500 times 0.92 to the power of x. And notice that this value, 0.92, 92 hundredths, it's between 0 and 1. Since it's between 0 and 1, it's going to cause the value of this car to decrease. And you can see that here in this graph. The question says, when will Sarah's car be worth approximately $10,000? In this case, we've been given the y value, and we're asked to find the x value that matches that. So with this situation, it's going to be much easier to use the graph. So this time, I'm going to find $10,000 on my y-axis, that's right here, and then just go down and see about how many years that would be on my x-axis. I notice my x-axis counts by 2, and I can see, hey, that's about 6 years. Sarah's car will be worth $10,000 after 6 years. It's not perfect, but it's a pretty good guess. So you can use that common ratio to see whether you have growth or decay. And the value you start with will be your y-intercept. So why don't you try a couple of examples? Pause the video, and when you're ready to see the answers, hit play again. So here's the answer to the first one. Our initial value was 2 miles. That's how far Roberta could run at the start. She increased her distance every week, so we know this is an exponential growth function, and that increase was by 20%. So we're going to add 20% to 1. 1 plus 0.20 is 1.20, or 1.2. So then we can write our function. f of x equals 2 times 1.20 to the power of x. When I substitute 10 in place of x in my function, I find out that after 10 weeks, she should be able to run 12 and 38 hundredths miles. And you can see that right here on the graph also. So pause the video and try scenario 2. So in the second scenario, Walter is trying to get rid of the weeds in his backyard, and he started with 217 weeds. The number of weeds is decreasing every day by 35%. So we subtract 35% from 1. That's 1 minus 0.35. That's 0.65. So that's our common ratio. Therefore, our function is going to be f of x equals 217 times 0.65 to the power of x. We want to know how many weeds he's going to have after 7 days. So we'll substitute 7 into our function, and we end up with about 10.6 weeds. So, somewhere between 10 and 11 weeds. He should just be able to go pull those by hand. The graph of my function here is teeny tiny, so let me zoom in a little bit. You can see that 217 is our y-intercept. That's how many weeds we started with at the very beginning. And then here, after 7 days, there's just somewhere between 10 and 11 weeds left.